Hello everyone. I welcome you all to this session. In this session, I'm going to discuss two very important things, semaphores and mutex. So let's start the discussion. As I have already written on the screen, what is semaphore is. We consider semaphore and mutex as synchronization primitives. So the meaning is we use semaphores and mutex when we are intended to synchronize two or more than two processes, right? So a semaphore is a programming construct used for controlling access to shared resource by multiple threads or processes in concurrent system. Okay, so that is the meaning of synchronization only. You do understand, right? A semaphore s is an integer variable. So in general, we consider semaphore as a kind of integer variable. It can contain integer values. Okay, so you just remember an integer variable, the semaphore is. Apart from the initialization, because for initialization we use a function, sem underscore init kind of function. So apart from that initialization function, we perform two operations. One is wait and another is signal operation. Okay. So there are other names also associated to these operations. Wait operation is also known as P operation, and signal operation also known as V operation. Okay. Signal operation also known as up operation, and wait operation also known as down operation. So these are synonymous to each other. At some of the places or in any of the question, you may find out wait or P or down. The meaning is same. Signal V or up, the meaning is same. There are two types of semaphores. I have already written here, binary semaphores and counting semaphores. Binary semaphores can have values 0 and 1, and counting semaphore generally have values starting from 0 to some n number of values. So counting semaphore you can consider positive integer. Okay. Although the operations wait and signal can be performed on either on wait, you can apply wait on binary semaphore. Similarly, you can apply on counting semaphore also. Okay. Now let's discuss how these operations we can perform. So I have written here the definition of wait and signal operations, or you can say P operation. So this is P operation and this is V operation. Okay, so please do remember, this is very important because in questions sometimes you find out P on V operation, sometimes signal and wait operation. Okay, so this is the operation wait. When let's say initially we have a semaphore variable s, and s is having a value associated to it, maybe 0 or 1 or 2 and so on. So if it is a binary semaphore, it will have only two possible values, 0 or 1. Whatever the value it is having, if we apply wait operation on it, the wait operation inside it, first this particular condition will be checked. Okay, so this condition will be checked, and the condition is if this value of s is less than or equal to 0. So in case this s is containing less than or equal to 0 value, this while loop does not contain anything, only one semicolon, right? So there's nothing to do. So again and again, if this condition is true, this semicolon will be executed, and again this condition will be checked. If this condition is true, there is nothing to do, so no operation, and then again same thing will be happening. So that means again and again this operation, this condition will be checked. If this condition is true, again this condition will be checked, because inside the while body there is nothing. Okay, but in case this condition is false, then the value of semaphore variable s will be decremented by 1. Okay, so ultimately when we apply wait operation, the value of semaphore variable, either it will be decremented by 1 or there will be a continuous loop running. So the process will be waiting in that loop. Okay. Now, what is signal operation? In signal operation, without checking anything, the value of semaphore variable will be given by 1. Okay. So in this structure, this was the very initial structure given in the books. In this structure, there was a problem we consider as bounded, or you can say busy waiting, not the bounded waiting. A busy waiting kind of problem is here. Why we consider this situation as busy waiting? Because when a process start executing this wait operation on any semaphore variable, and let's say s is having value 0, if s is having value 0, this condition is true, and this loop will be continued and executing. So the process will not be able to do the fruitful thing again and again, the same condition it will check. So process is doing and consuming the CPU cycles without doing any fruitful things. So that is busy waiting. The process is busy in doing something, but ultimately it is waiting to happen some particular event. And process is waiting to increase the value of this semaphore variable s, 0 to 1, right? So to enhance this particular situation, to deal with this situation, this operation and the definition of semaphore variable has been modified. Okay. So this type of semaphore is also called spin lock. Spin lock because process is spinning. Okay. While waiting for to acquire the lock on the semaphore. So spin means again and again the process is stuck in a loop, and again it is executing that. So it is also known as spin lock. You can remember that. Now look at the modified thing. Modified definition of semaphore as well as the wait and signal. Why we are looking for modified definition of semaphore? To avoid this busy waiting kind of situation. So the modified semaphore, instead of having a single variable, there is a structure of the semaphore. So type def struct has been defined. Type def is a keyword. You know that if we want to define our own data type, we can use type def, right, in C programming. And semaphore is the name of this structure which we are defining. And this structure is having a value, and one process list is also there. Okay. So what is happening in wait, or you can say P operation, we are passing the address of a semaphore variable, and then the value of that s variable or semaphore variable s is decrementing by 1. Right here we are not checking the condition. After decrementing we are checking the condition. If that value of s is having less than 0, in that case the executing process will be blocked. So this process will be added into a, you can say, blocked list, s list, and the process will be blocked. So the process will be blocked. Why we are blocking the process? Because in the previous case the process was not blocked, it was keep on executing the while loop, and it was consuming the CPU cycles, right? And that was the reason of busy waiting. So we want to avoid the busy waiting. So when a process is trying to do the same thing, the condition, and it may be stuck in that particular loop, we are blocking that process. Okay, so that is the modified structure of wait operation. Now look at the signal. So because we are blocking the process here in the wait operation, we will unblock the processes in signal operation. So signal, again we are passing the semaphore, and we are incrementing the value of semaphore by 1, and then we are checking if this value is, you can say, greater than or equal to 0, not less than or equal to. Here it should be greater than or equal to, so I'm making it greater than or equal to. So if the value is greater than or equal to 0, then we remove the process P from the list, or you can say blocked list. So the process will be removed from the block list and the process will be wake up. So I hope as a programmer you understand how we can block a process and how we can wake up. We can use different system calls. Okay, so in case we want to block a process, we can use either kill system call with a signal sig stop. Okay, and if you want to unblock the process, we can use kill system call with sig cont. So I'm not going into the programming detail as of now, you just try to understand this logic. Okay, we do the programming in lab, so when I prepare the content for lab, then I will elaborate syntax wise. Okay, so by utilizing this modified definition of wait and signal, we can avoid the busy waiting kind of situation, right? So when we do the C programming in lab, we will be using these functions. So to define a semaphore variable, like name is mysem or mysemaphore, sem underscore t is the data type. And to initialize the value of semaphore, we use sem underscore init function, sem underscore init, and we pass the address of semaphore. In case the semaphore variable we are going to utilize as shared semaphore variable, then we set this argument as 0, and then the initial value of the semaphore we can give. So generally we can give either 0 or 1 or any other value. So we can initialize the value by 0 or 1, right? Sem underscore wait is the operation which I have elaborated, wait operation, and post is the signal operation actually. So in C programming we call sem underscore post, it is the signal operation. Okay, so signal I have already elaborated. Signal will increment the value of semaphore by 1. Okay, and this wait decrement the value by 1. And in case we want to destroy the semaphore variable, we can use sem underscore destroy. So please do remember these functions. It will help you to program. Now let's discuss the mutex. Mutex is also very important synchronization construct. So the short form it is, and the full form you can say mutual exclusion. So mutex provide mutual exclusion. It is a synchronization object used in multi-threaded programming to ensure that only one thread can access a shared resource. So we use the mutex in case of we create multi-threaded process. Okay. Such a variable used to block a particular thread for a certain duration, and it can ensure the mutual exclusion. So mutex can ensure the mutual exclusion, right? In C programming, we use a number of things. So to declare this mutex kind of variable, we use pthread underscore h header file. To initialize the mutex variable, we use pthread underscore mutex underscore init function. And on mutex, we can perform two operations, locking and unlocking. So to perform the locking operation in C programming, we use pthread underscore mutex underscore lock. For unlocking, we use pthread underscore mutex underscore unlock. Okay. For destroying the mutex, we use pthread underscore mutex underscore destroy. Okay. So please do remember. So in case we want to declare a mutex, we use pthread underscore mutex underscore t type of variable. And this is the variable name, my mutex. Let's say I have declared. If we want to initialize this my mutex, there is a function pthread underscore mutex underscore init. So we can pass that my mutex inside it, or my underscore mutex we can initialize by calling a macro. So this is a macro. I'll tell you how to initialize a mutex in lab session, so don't worry as of now. Pthread underscore mutex underscore lock to acquire the lock on the initialized mutex, and you pass the address of that. And in case after critical section we want to release the lock, then we use unlock function. And in case we want to destroy the mutex, then we can use pthread underscore mutex underscore destroy. So your mutex will be destroyed. You pass the mutex here, which mutex you want to destroy, right? Okay. Now look at the fundamental difference between the mutex and semaphores. In terms of definition, you understood what is the difference. The mutex object serves as a lock. So mutex serves as a lock or unlock. There are two mechanisms we perform on the mutex. We can lock or unlock the thing. Like we have the lock on a door. So if we don't want anyone should enter inside the room, we can lock that, and only we are having the key, so we can unlock that. So mutex follows the similar kind of mechanism, but semaphore follows different thing like signaling mechanism. So if I talk about the public toilets in trains, when somebody is using the toilets or someone is inside, that red light start blinking. Okay, when someone will come out and toilet is available, the green light is start blinking. So that is signaling kind of mechanism. It is not locking. Locking mechanism is also there in the toilet, but there is a signaling mechanism also there. Okay, and both kind of mechanism we can use to synchronize the thing, right? So I hope you can understand. So semaphore is a kind of signaling mechanism, like traffic light, we show the signals, and to control the traffic we can use boom barriers also. That is locking mechanism. We can block the traffic by putting the barrier, so that is locking. We can install the traffic light, so if we switch on the red light, the traffic will stop. That is signaling mechanism. Okay, mutex is an object and semaphore is an integer variable, right? So please do remember. Then function mutex enables the multiple programs, threads to access the shared resource, but not at the same time. So it ensures the mutual exclusion. Okay. Semaphore enables multiple programs or threads to access a finite set of resources. So if there are n number of resources, we can set the semaphore and start applying the wait operation. Once the semaphore will become 0, no further wait can be applied, right? The process that has acquired the lock on the mutex. So mutex has a kind of ownership mechanism. If I am locking the door, only I will be able to unlock it. But in semaphore, it is not the restriction. Let's say process P1 is applying wait operation, P2 can apply signal operation, right? If P1 is applying signal operation, P2 may apply wait operations. So there is no boundation that on a single semaphore, when a process Pi is applying wait operation, only Pi should apply wait operation. There is no such restriction. So ownership is not claimed in case of semaphore, but mutex having a locking unlocking mechanism, it has the ownership. So when a process locks it, only the same process can unlock it, right? So please do remember, this is very important thing. Categorization, mutex doesn't have the further categories, but the semaphores has the counting and binary, two types of semaphores. So counting semaphores and binary semaphores. Operation I have already told you. On mutex we can use locking operation and unlocking operation. Okay. And on semaphores we can use wait and signal operation. Right. So let's say we want to synchronize few things. Let's say there is a statement S1 and there is another statement S2. Okay. Now these two statements, two processes are executing. So let me wipe it out and try to understand. Process P1 is having one statement S1 and process P2 is having an statement S2. Now we want to synchronize. What we want actually, before execution of S2, S1 must be executed. Although these two processes P1 and P2 are executing concurrently. So to resolve such kind of issue, we can have a shared semaphore or maybe mutex lock, you can say. So here let's say I am declaring a semaphore. So sem underscore t type of variable you can declare. Let's say I am having s is one of the variable which is of semaphore variable. Okay. So don't focus on syntax as of now. Just you consider s as a semaphore. Now, if initially you assume that I initialize this semaphore with 0 by utilizing sem underscore init function, right? So it is having value 0. Now if I want this S2 should not be executed before the execution of S1. So what I can do is I can apply wait operation here on semaphore S. Now because initially semaphore is having value 0 and this wait operation try to decrement the value of semaphore, and you know that inside the wait operation there is a condition. If this semaphore is having value 0 or maybe less than 0, there is a loop, or the process either will be blocked or it will be in loop. Okay, so it will not be able to execute this S2, right? So in order to come out from this waiting situation, there has to be a signal operation performed on this semaphore S. So after S1 I am writing here signal operation. So if I signal here S, that means if first this process try to execute, this process will stuck here because S is having initial value as 0. But let's say context switching happens and the P1 start executing, then P1 will execute S1 and then this P1 will signal this semaphore variable S. So the value of S will become 1, and once the value of S will become 1, this P2 will be able to execute this statement S2. So in such a manner we are synchronizing this order. First S1 will execute, then S2 will execute with the help of semaphore. I hope the use of semaphore and the definition of semaphore is clear, right? So I am closing this session. See you in the next class. In the next class I will solve few problems on the similar concept. Thank you everybody.